You mean H1B or um, getting women into STEM? I don't think they want to lower the standard because that is not in the interest of the businesses. So I don't think they want to lower the standard, but they want more people to be available. So when you think about it, okay, looking at this class, okay, we are 100% guys, okay, which is kind of rare because usually you get like one or two women in classes. Um, so if you think about it like this, then you're asking, but we know in population it's about 50-50%. In fact, I think there are slightly more women than there are men. Okay, that's the genetic pool thing. Um, so the idea is if we can somehow mobilize and have women to get into STEM as much as men does, then your workforce is 2x as strong as it is now, and then Google doesn't have to pay as much money anymore as salary. Yep. That's interesting. I did not know that it was initially more women. Ah. Mm-hmm. So, so that's very interesting. So anyway, I'm not going to spend any more time on that particular topic. But if you're interested and you want to support the movement to have more women in STEM, or at least make it not as hostile, okay, to women, to get into the field, go to the meeting on that day. Oh, by the way, lunch is supplied. So there's a link. Okay, I'll send you guys a link. So lunch is supplied if you register first. So you're gonna have to go to the link, register, and then it is from 11 to 1 o'clock on Friday. Is that okay? All right. Okay, so we can now go back to the discussion of graphs. Last time we kind of talked about the concept of graphs, but we didn't really quite introduce, I did not introduce the formal definition of a graph last time. Yes? This is not updated yet. So the A star is still not there. The A star algorithm that I put in here, is not going to be the usual A star algorithm, so it's going to be a little bit different. But I will put it there for sure. Okay. So the graph itself is represented as a G. Okay, so typical name for a graph is G, but it's a two tuple. Okay, so when you look at these parentheses, it is representing it's a two tuple. The two tuple consists of two different sets. The first set is V, which stands for the set of all the vertices, and then the second set is the set of all the edges. Okay, so what is a vertex and what is an edge and how do they relate to each other? So now we look into how they relate. So the first thing we notice is this one here. The set of edges is a subset of the vertex Cartesian product with itself. Okay? Okay, so let's just stop here. Okay? Let's just stop here and we'll use a few examples to illustrate what I mean by that. This is the problem of having classrooms right in the middle of a parking lot. We're basically an island inside the huge parking lot. And we know how many people like to make their exhaust sound louder than they have horsepower. So, hmm? Seven? Civics and coffee cans. Yep. I believe so, but let's double check. It doesn't hurt to double check. Yep, I am recording and the voice is up. Okay, but it's good to check. Thank you. All right, so we'll go ahead and just say that the vertex set has, I don't know, let's pick only 3 vertices. So A, B, C. You can use anything as vertices. Okay, I'm just using simple letters, as vertices. You can have numbers, integers as vertices. You can have coordinates as vertices. So it doesn't really matter what a vertex is. It is just an element of the set V. That's all. Is that okay? Yep.
Can you, from the G function, can you actually create a graph from there instead of
Create,
adding it to the function?
say that one more time.
Can you create with the G, with the tuple V and E, can you create a whole entire graph from there, or do you have to reach from an actual graph and map it to that function?
Well, let's see where we can go from here, and then we'll go back to that question. Okay. So now we know E has to be a subset of, okay? So it has to be a subset of the Cartesian product of V with itself, okay? So we know it is going to be AA, AB, AC. Now you probably know what's going to go on here. So we got BA, BB, BC, because we are looking at the Cartesian product of V with itself. So we are looking at every single way to pair up the elements, even with itself. CC, and that's it. Okay? So E, the only requirement of E, or the set of edges, is that it has to be a subset of this, and not even a proper subset. It can be actually the same as the Cartesian product itself, where we have a fully connected graph in that case. It can also be an empty set. In other words, you can have all the vertices and no edges whatsoever. It's still a graph. Now, how useful is that graph is questionable, but technically, is it a graph? Yes, it is a graph, because an empty set is always a subset of something, or a subset of another set. Is that okay? All right, so in this case, we're going to make an actual definition here. So we'll just say that E is, okay, we'll just say that AB is an edge in it, BC is an edge in it, and I'll just say that CA is an edge in it. Okay? All right? So if I do something like this, then I can actually visually draw the graph. Do you guys want me to use the tablet to kind of show the graphical representation? I think it's going to be helpful. Let's do that. So that set of rechargeable batteries actually lasted a long time, since I bought the mic, the 2 rechargeable batteries has lasted that long, basically. So it's not bad. Now I have to remember to recharge the ones that I have taken out, and so next time I'll have rechargeable batteries available again. So there's that. All right. And we want to get to lecture notes. I know you cannot see anything. I'm just setting up right now. Okay, there we go. All right, so now we go back to this side and make the connection. And this morning I had an interesting job with the on-campus theater. They had all of the projectors these days. Why is it playing? I have no idea why it's playing, so I apologize for the distraction, unless you guys want to continue to play. The speaker is not that good. Next time I'll bring up proper speakers, then we can actually play it. I hate it when the bass is not there. You guys know who is the composer? It's recorded actually. I think the mic actually picked it up a little bit, not a whole lot. Okay, so I'm just making this a little bit bigger. All right, so we'll go back to the text representation of the graph and drag this one a little bit below that. Okay, there you go. All right, so we have vertices, A, B, and C. So vertices typically are just points, okay? So in the actual graph representation, we have 3 points. We'll label the points A, B, and C. The edges, on the other hand, are directed. In other words, unless I say explicitly that a graph is not directed, they are directed. So in this class, we are only going to deal with directed graphs and not undirected graphs. In the directed graphs, edges are, they're directional. So in this case, the edge that we call AB is going from A to B. So when we draw A to B, it is an arrow that is going from A to B like that. It is not showing anything. So I think it has lost connection. Okay, let me disconnect. Yeah, we have to plug it back in and reconnect. Try to reconnect. I think I've tried it before and that did not seem to work. There we go. So let me move it down a little bit again because we want to look at the text representation while we look at this one. So we'll click this one out of the way. There we go. So the edge AB is an arrow going from A to B. So now we can actually see how to finish the entire thing because we got BC as an edge. So we have BC as an arrow going like this. And then we got CA as an edge going like that. So are there any questions about the text representation as opposed to the graphical representation of the same thing, the same graph? Yep. Uh-huh. If you have a non-directional graph, it wouldn't be a tuple. It would be a set. Which also means in a non-directional graph, you cannot have an edge going from a vertex to itself. Because if it's going to be a set, you can only have one element. Yep.
So could you have like another tuple in there called BA and it would just be like
Yes.
yeah,
Yep, you can definitely have that. So the question is, if we go back here, okay, and we say, okay, we're going to include another edge, right? So we can have BA. Then when you go to the graphical representation, okay, there you go. So in the graphical representation, we are getting the edge that is going from B back to A. So B back to A is this new edge, and it is considered distinct and different from the one that is going from A to B. In the set representation, it's pretty clear because the tuple AB is not the same as the tuple BA. You guys okay? Yep. So in the tuple, order does matter. So that's why AB and BA are considered distinct elements. Yep. The direction is important, but in this case, it's not a vector in the sense that you're numerically encoding, the direction. In fact, by the time we get to planar graphs, we'll understand that sometimes it's not possible to draw a graph without crossing, the edges crossing each other. So we'll get to that point when we talk about planar graphs. Yep.
So non-directional graphs would be the exact same thing without the arrows. So it's just like a
Correct.
bunch of
Yep.
data points.
Yeah, but in a non-directional graph, you wouldn't have AB and BA being two edges because they're just the same. Yep. But in this class, we're only going to talk about directional graphs because the application of directional graphs are a little bit more than non-directional graphs. A directional graph is also called a digraph, D-I-G-R-A-P-H. The DI part stands for directional. So if you see the name digraph, it means it's emphasizing that it is directional. All right. So are we still okay at this point? All right. Cool. So getting back to the notes. So we are moving along. So we have some terms here. Not really a lot at this point. So a path in a graph is a tuple of vertices. Edges from E must lead from one vertex to another vertex. This is technically not it is not the definition of a path, but the definition of a walk. W-A-L-K. Okay, so we'll get into those terms, when we need to, but I don't want to kind of throw out all the terms just for the sake of the terms. Okay. But a graph has one extra requirement. In addition to all the vertices being connected by edges, there's one more requirement. You cannot repeat a vertex nor an edge along the path. So let me say that one more time. You can look at the graph, you can look at the path as a sequence of vertices, okay? And between every two vertices along the sequence, each adjacent pair of vertices must be connected by an edge that is found in E. Is that okay? But that is actually the definition of a walk. A path is a walk with no repetition of vertices nor edges. Is that okay? So I'm going to change my notes and fix that. Okay, so a path does not have repetition, so there are no loops in a path.
Says it under it, right?
Yeah.
Path cannot contain duplicates, but it's not explicit.
Yeah, it's not that explicit, so I'm just making it extra explicit. Okay, so that's all we need to know, in order to understand Dijkstra's algorithm. So Dijkstra's there's one more thing. There's one more thing, which is a cost associated with each edge. So in addition to knowing what is the origin and what is the destination with each edge, you can also associate a non-negative number as what we call a cost to that particular edge. In other words, if you look at edges as one connection from one point of a map to another point of the same map, then the cost can be associated with, it can be an overall cost, which includes the time of the driver, insurance, fuel, and all that stuff. But you can also have just a particular number, like time. Okay, so it depends on what you're optimizing, and that defines what the cost is. Okay, so we're going to look into Dijkstra's algorithm. So we're kind of like jumping into Dijkstra's algorithm in order to understand what it is and how it gets the job done. Dijkstra's algorithm is an algorithm that can find what we call the shortest path from all vertices to a particular set of destination vertices. So it's really interesting in that particular way because it is not really just finding a single shortest path from one particular vertex to another vertex. If you tell me what the destination vertices are, okay, it will find the shortest paths from every single vertex to a destination. Okay, now that sounds really abstract, so let's de-abstract it. Okay, think about yourself going to Six Flags, okay, a theme park. A theme park has, do you think theme parks only have one bathroom? Well, maybe in some other countries, but not in America. Okay, exactly. Well, no, it's not going to be a very long line. It's just that the whole park is going to stink. I'm not going to go any further than that. Okay, but we'll just say that there are multiple bathrooms. Okay, so each bathroom can now be designated as quote unquote a destination. Is that okay? And then you have all of these visitors in the theme park, and they all want to go to bathrooms. Dijkstra's algorithm, if each visitor and each bathroom is considered a vertex, the Dijkstra's algorithm will find the shortest path for everyone to go to the closest bathroom. That is what Dijkstra's algorithm can do, or will do. Is that okay? So is that analogy working? So it's not about a particular person going to a particular bathroom. You can have like 10 bathrooms in a theme park. it will figure out which one ends up to be the closest one and how to get there in the shortest amount of time. But it doesn't only to do it to one single person, it will do it to everybody. Yep. Okay. So what we'll do now is to look at the representation, what is the input of the algorithm and what the variables are in the algorithm. So we are just using this same notation that we have already introduced earlier. The graph that is of interest to us is G, and G has V as a set of all the vertices and E as a set of all the edges. And in addition to that, we have a D, or distance function. The distance function is a function that maps E, the set of all the edges, to the set of non-negative real numbers. Okay? There's a particular problem with negative distances, because negative distances sometimes will lead to loops. Because if you think about the summation of all the edges in the loop being negative, then the more times you go through the loop, the better. and it doesn't reflect actual real life situations. So that's why I want to emphasize that we want to make the distance function map to non-negative values. Can be 0. 0 is okay. That's not a problem. But negative values is a problem. Is that okay? So that's what the R star or R asterisk is representing. It is non-negative. And then we have a subset inside V. So S as a subset of V is a set of vertices identified as destinations. So in our example, the bathrooms, the locations of the bathrooms is basically the set S. Is that okay? Now, in many situations, there's only one single destination that you're interested in, but you can also have any number of destinations. As long as this is not an empty set, it will still be good. If it's an empty set, then Dijkstra's algorithm cannot really work, because there's no destination to go to. So there's nothing to do with Dijkstra's algorithm. So this is actual code. Okay, it's initialization. So for each vertex that is in the set of the destinations, we are going to assign a 0 to L of V. So L is the length, which is basically, cumulatively speaking, what is the summation of the distance of all the edges to go from one vertex to another vertex. Is that okay? But it is more specific because it is the length of the path to go to a particular destination. Okay, so let me flip it around and ask this question. If I have a particular vertex V that is a destination, how far is it away from a destination? 0. That is why we initialize the length of the path to a destination to be 0 for the destinations themselves. Is that okay? So the rationale, I want to explain the rationale in addition to what the code is saying, because once you understand the rationale, you go like, oh, okay, so the other part is just syntax to describe that. So what about all of the other vertices? So for all of the other vertices, I'm reading this particular line here. So for all of the other vertices, which is vertices that is in the set of V minus S, so we are talking about all the vertices that are non-destinations, then we initialize. Okay, this is just initialization, but we initialize L of V, or the length to go to a particular destination, to be infinity. In other words, we don't know. Okay, we haven't explored yet. So at this point, I'm just going to say, okay, Jimmy, I'm sorry. To go to the closest bathroom, you will need an infinite amount of time. Of course, Jimmy's not going to be happy about that answer, but we'll try to figure it out. Yep. It just has to be a value that cannot be, no other value can be more than that. So regardless of the representation, there's always a value like that. So if you, a maximum value for integers, and then there is an actual infinity representation with double precision floating point numbers. So in the comparison, if you have a value, a variable that has the quote-unquote infinity representation, then it's going to be greater than everything else. Yep. Yep.
The stdio header does have a maximum
But that's for integers. For real numbers, you need floating point numbers, and there's a representation of an infinity and a negative infinity for floating point numbers. Okay. So are we good so far? We're just initializing the L value, the length, to a destination for all vertices. If the vertex is a destination, then L of V is going to be a 0 by initialization. And if V is not a destination, then we use infinity to initialize L of V. At least that's what we know at this point, because we have not explored anything yet. So now the next thing is I'm initializing another set called Q. Q is a set of quote-unquote boundary vertices. These are the vertices that are of interest to me, because somehow they are connected to a destination. They're known to connect to a destination. Is that okay? So, other than that, I can't really describe Q more than that at this point. But the initialization of Q is we are just taking the set S, which is the set of all the destinations, and use that to initialize Q. Because remember, Q is representing a set of vertices that are known to connect to a vertex, to a destination. So a vertex is definitely connected to itself, and that's why we initialize Q with the destination vertices. Okay. And then we initialize E prime to be an empty set. So E prime is a part of the solution. So eventually E prime will consist of the edges that make up shortest paths from each vertex to a destination. But initially it is initialized to an empty set because hey, we haven't even started with the actual algorithm. So that's why it's empty at this point. Is that okay? All right. So with all the initializations done, now we can actually focus on the algorithm itself. I'm using items or bulleted items to represent the algorithm, and that's why it looks a little bit like Python without the open and close curly braces. So indentation is the only indication of how it is nested. Okay. So the algorithm says as long as Q is non-empty, we got stuff to do. Okay, so as long as there are vertices that are known to connect to a destination that we have not concluded yet of how it connects to the destination or how other things may go through them to get to the destination, we got stuff to do. Okay, so this is a good time to kind of go back to a graphical representation. So I'm going to start a new page. So let's say we got some destinations here. Okay, so this is D1, D2, D3, and they are destinations. The set of Q, okay, so we'll kind of use this to represent the set of Q. So the set of Q is made out of vertices that already have known paths to the destinations. In other words, how these vertices connect to the destinations is already known. Okay. So we already know these paths. We already know how they go. But what we do not yet know is how other vertices can go through the vertices in Q to connect to the destination. Q is representing the frontier. Okay, so if you think about Dijkstra's algorithm as an exploration process, Q is the frontier. The frontier starts with things that we already know, which are the destinations, and we slowly expand the frontier. Okay, frontier expands and expands and expands until the frontier until we know everything about all the vertices. So that's one way to look at the set Q. It is the frontier of exploration. Is that okay? Yep.
So it'd be perfectly possible for Q to never reach another vertex, to never reach certain vertices.
That is correct. Yep. But the algorithm will still conclude because, correct. There will be no edge in E prime that will lead that vertex to a destination. That is correct. So the rest over here is, I'll just say, unexplored. This is the frontier. And this portion is, I'm just going to use this word here, just explored. You cannot see it. So this is a little bit counterintuitive because we are starting the exploration from the destinations. Okay? In other words, if you think about the map of the theme park, what we are doing is we're starting with all the bathrooms. And then we slowly expand, the frontier radius from the bathrooms so that we can tell each little boy which bathroom is the closest and how to get to that bathroom. Is that making any sense? All right. Okay. So getting back to the algorithm itself. So if you know that Q is not empty, then the first thing we know is we're going to pick one element V in Q. Okay, we can do it. We know for sure that if we get into the loop, Q is not empty. So there's at least one element in Q. Okay, but we are not just randomly picking one of the elements in Q. We are picking one element in Q such that, okay, so let me see if you guys know how to read this. What is the easiest way to describe this statement here? For all W in Q, L of V is less than or equal to L of W. What is that saying? Not zero, because at this time we don't know whether there's zeros or not. Yes, exactly, that is what it means. Okay, so you're looking at all the elements in Q and go like, okay, which one of you has the lowest or the smallest L value? Okay, in other words, it's looking at the closest boy to a bathroom. You got several boys in Q, and then you're saying, okay, who's closest to the bathroom? I am closest to the bathroom. Okay, you're picked. Is that okay? So once we pick once we pick the vertex V, then we perform this operation, which is basically just removing vertex V from Q at this point. In other words, you're no longer in the frontier because we are now asking you to explore. Okay. I use the left arrow symbol to represent assignment instead of a single equal symbol, because when I'm talking about pseudocode like this, a single equal symbol can be just equality. So am I saying that it equals to that, or am I actively changing and updating something? And that's why I use the left arrow to mean assignment, which is basically saying evaluate the right-hand side and then update the left-hand side. I'm not expressing they are equal at this point. Okay. So once I remove V from Q, then what I'll do is to do something like this. So let me just explain what this syntax means. For each E in a particular set, do the following. Means, if I have a set like this, I'm going to perform these operations for every single element in that set. So now the key is, which set are we talking about? So let's focus on the set itself and find out what it is talking about. So we're just focusing on the set. So the set basically says, okay, each element is a 2-tuple, and each 2-tuple looks like WV. This V is already bound. In other words, we know which vertex is this V because we picked that earlier. So we are really looking at edges that is going to V, the vertex that we have chosen. Is that okay? So the rest, this is just really saying that they have to be in the set of all the edges, because otherwise you can pick an edge that is not in E, so that would not be useful in the algorithm. So in other words, we're looking at all the incoming edges to V, the vertex that we have chosen. Is that okay? Now, that is important because in order for V to be in the set Q to begin with, V itself already has a shortest path to go to the destination, to go to a destination. Is that okay? So now we are looking at all the incoming edges into V. In other words, we are now saying, okay, who else can go through V to go to a destination? We're exploring everybody that can go through V to get to a destination. Is that okay? All right. So in the next statement, I'm saying, okay, so let's say we pick a particular edge, and that particular edge is going from W going to V. Okay, I'm just giving it a name so that I can refer to W later on. So the first thing we need to do now is to say, let's evaluate this expression and see whether it is true or not. So now the question is, okay, so what is this representing? It's a comparison, and it is comparing this particular sum with this particular value. So the first thing we want to do now is to evaluate this particular addition and say, what is the meaning of this? Okay, L of V is the length of the shortest path from vertex V to a destination. And that is known already because V is in Q. D of E is the distance of a single edge, E, which, and that edge is going from vertex W to vertex V. In other words, we are asking this question. If W is to go through V to go to a destination, what is the distance or the length of that particular path? That's what the highlighted portion is asking. Is that okay? On the right-hand side of the comparison, we are now asking, hey, what is the length of the known shortest path from W to a destination? Because it is possible to have a W that already has been explored before. That's entirely possible. We'll talk about that later. So this is basically saying if the length of the known shortest path to go to a destination, I'll have it just a bit later, from W to a destination is more than the length of the path going through V to a destination, we got stuff to do. Because what we thought was the shortest path is not the shortest path. Yes, go ahead.
For the first time, like let's say W has not been like explored at all. It starts at infinity, right? So in that case, this you would also use it for like the initial assignment.
Yes.
Yeah.
Yep. So when W is not explored at all, and it has a L value of infinity, then this comparison is guaranteed to be successful, to be true. So you would update it. But it is also possible that W stays in Q, but somehow got updated along the way. And then you need to figure out, okay, are we finding a shorter path or not, right? So we can design certain graphs, to trigger this to be true or to make it false. Okay. So let's say it is true that we have just found a shorter path for W to go to a destination. The first thing we do is let's update it. Okay. Because L of W is supposed to be the length of the shortest path from W to a destination. If we know that if W goes through V to go to a destination has a shorter length than what we knew before, we need to update it. Is that okay? And then the next thing we do sounds a little bit confusing, so we'll go ahead and look at this one. And let's see, am I doing this correctly? Okay, so this is correct. All right, so I'm just double checking because I knew that I made a mistake last year in this algorithm, so I want to make sure that it is corrected. It is corrected. So this particular thing is saying, okay, if we have edges in E prime that starts with W, let's erase those edges. Why do I need to erase those edges? Because those edges are representing an old path of a lengthier path. Okay, that's the best way to describe it. So WU, if it already exists in E prime, is a part of a lengthier path to a destination than what we have now. Okay, so we are basically taking an eraser and go like, whoops, that was not the shortest path. So we take out the edges on what we thought was the shortest path, but is not the actual shortest path, so that we can redirect it. So this is erasing, and then this is adding back the actual edge that will be a part of the shortest path from W to a destination. Does that make sense to you that the edge WV should be in the solution graph? At least at this point. Maybe later we'll find something even shorter and take this one out, but at this point we know that this should be a part of the solution. Is that okay so far? Okay. And then the next thing we do is we are going to make a union. In other words, we are expanding the frontier. The frontier used to end with V, but now it is ending with W. Because we know for sure that W connects to a destination, and not only that, the length of that shortest path was just updated. So I have to put W back into Q so that everything else that connects directly to W can now be reevaluated. Is that making any sense? If one particular vertex has a L value updated, then everything that connects to that particular vertex may potentially have a shorter path now. So they all have to be reevaluated. And putting W back into the set of frontier vertices will trigger that reevaluation of other vertices connecting to W. Is that making any sense? Yep.
How do you update W?
Hmm?
No, not W, U.
U?
Because you have it in there.
You mean here?
Yeah.
This one? U is not bound by earlier statements. So basically, you're just going through the entire E prime and say, okay, which edge of E prime starts with W? Take it out. Yep. Okay, but that's a good question. It has to do with when a particular variable is bound to a particular constant. And the thing about U is it is unbound. It is only bound when you run this loop. Okay. So are we still doing okay so far with the explanation of why we are adding W as a vertex into Q, which is the set of all the frontier vertices? We good with that? Okay. Cool. That's the entire body of the for loop, which ends the while loop, which is also the last statement of the while loop. So we keep doing all this stuff until the while loop is done, which means until Q is empty. And then we just say, oh, okay, we're going to define a new graph, okay, G prime. G prime is going to have the same vertices as V, which is the original graph, but the edges of G prime is only E prime. So the new graph that we are creating, which is G prime, is quote unquote the solution graph. If you look at the solution graph and you start with any vertex, there's only one way to follow the edges, and it always leads to a destination. And then when you follow those edges, it's always the shortest path. Which is kind of interesting, because what do you think G prime is going to look like? First of all, do you think it's going to be a tree or a forest? What is the property of a tree? What makes a tree different from other graphs? Okay, let's draw some pictures. Okay, so I'm going to draw some pictures here. Okay, switch to the tablet. So with a tree, okay, so I'm not using any direction right now. This looks like a tree, or can be seen as a tree, right? Now, one thing that's interesting about a tree is you can pick any vertex and make it a root and hang it up, and that becomes a tree. You can take any interior node, you can take any leaf, and you hang it up using that particular node or vertex, and that looks like a tree too. So that's a really interesting property of a tree. Okay? What makes it not a tree? What makes a graph not a tree? That is not a tree. Yep.
You could also have a vertical path connecting to one of the leaves, and that makes another tree.
Yes. So what makes a tree a tree? There's only one path, okay, up to one path from one vertex to another vertex. Okay? So now the question is, if you look at the solution graph, the solution of Dijkstra's algorithm, if you look at G prime, do you think that's going to be a forest? Oh, by the way, what is a forest? We know what a tree is. What is a forest? A bunch of trees. That really is, that's what it is. So if you have a whole bunch of trees together, it becomes a forest. Okay? So the question now is, do you think whether G prime is going to be a tree or not? In other words, when you look at G prime, can you have two different paths going from one vertex to another vertex? That is the question. Okay, the answer is no. Okay, that's correct. That is correct. The correct answer. Why? If you just look at the algorithm, can you tell why that is the case? I think you got your hand up first, and then you. Yep, go ahead, and then Sean. No, they don't have to be. You can have equal distance shortest paths, but only one is going to be represented. But why only one is going to be represented? That is the question. Yep.
The G will be, it'll have all the vertices, and each vertex will have a path to the destination, right?
Say that one more time. Sorry, I didn't catch.
So the algorithm will produce like the graph G prime, and then it'll have all the vertexes of the original one, but they all somehow lead back to the destination.
To a destination, correct.
So,
If there's a path. If there's no path, then the vertex may be not connected.
so like, as you choose 2 points, they're like basically opposite sides of the destination, and they'll kind of go their own path to the destination. So
Yep.
two shortest paths, say from like you choose one vertex and the other one's on the other side, and you'll have both of them leading to the same thing, but there's two paths connecting to one, and that's the destination.
Okay. But then the question is, why can't I have two paths going from a single vertex to the same destination?
Because there's only one shortest path.
No, they can be equal distance. I can design a graph, where two paths have exactly the same distance and they're both shortest. You're next because he had his hand up, in the previous.
Okay, because we only update the path if it's like less than the one that's like already
Yes.
there. So if you find a path like that's like another shortest path, it just won't like the algorithm won't add it.
Okay, that's a good valid reasoning leading to the conclusion that we can only have trees or a forest as G prime. But let's listen to what. Yep, go ahead.
That's what I was going to say.
Oh, okay.
It'll just have, if it has two of the same, it'll just have the older one.
Well, the key actually has to do with this for each loop, because every time we make a correction, we erase an edge first. Without that, then you can have multiple paths from one vertex to the destination. But with this, we guarantee that there's only one edge. There's only one outgoing edge for each vertex. Yep. Because if W had outgoing edges in E prime before, we erase all of those and replace it with a single edge. That is what guarantees that we will end up with a forest. Yep.
So you could use this algorithm to solve the traveling salesman?
Traveling salesman problem. Let me think. No, it does not solve that particular problem. Okay, the traveling salesman problem. Let me present the traveling salesman problem first so that the class understands the context. So the traveling salesman problem, okay, if I graphically represent it, looks like this. Okay, so I'm going to use a very simple version of that. You have 5 cities. Okay, you got A, B, C, D, and E. And the traveling salesman problem is asking, what is the best route to traverse all the cities and have it being the shortest? Which is not the same as asking, how do I go from A to C using the shortest distance? So the traversal problem is a little bit harder because you have to basically visit every single city, but you have to find the shortest path that can visit all the cities and still be the shortest at the same time. Dijkstra's algorithm says, hey, I can get you to the closest bathroom, but I want to go get, cotton candy. I, I want to look at the dolphins. I want to pet, those, animals over there, and still want to go to the bathroom as quickly as possible. Give me that route. Dijkstra's algorithm cannot do that. But the traveling salesman problem is, doing that. It's basically saying, okay, I want to do everything in a theme park and walk the least distance. Yes.
I was gonna say the red maze one would be like an example because you have
To do what?
with the Dijkstra's
With Dijkstra's algorithm? Yes. Dijkstra's algorithm is also known as breadth first search. Okay? Because you're expanding the vertex that has the shortest path to a destination first. So that's why it is also known as breadth first search. So it's basically doing a breadth first search for all the vertices, so that by the time you're done with that breadth first search, you will know the shortest path from every single vertex to a destination. Is that okay? Make sense? Okay. All right. So that was a good question. Whether Dijkstra's algorithm can solve the traveling salesman problem. The traveling salesman problem is also what we call an NP complete problem. Does anyone know the term NP complete? No? Okay, so do you want to give it a shot? Go ahead. No?
I think one thing I didn't know about it is that pretty much almost any NP complete problem can be converted to a different one.
Mm-hmm.
If you solve one of them, you've solved all of them.
Yes.
And that's kind of a problem because I think aren't passwords also NP complete problems?
Okay, so a quick search of NP complete gives us a very brief summary of what it is. So in computational complexity theory, which is a upper division class in undergraduate computer science, which means most of you will take that class, it's a math class, but worse than this. Well, I would say more fun if you like that sort of thing, but it's worse than it if you don't like the math stuff. Okay, so NP-complete decision problem is belonging to both the NP and the NP-hard complexity classes. In other words, they are defining classes of problems where the complexity of transforming from one problem to another problem is polynomial time. But the known best algorithm to solve a problem is NP, okay, non-deterministic polynomial time. Okay, NP stands for non-deterministic polynomial time. Okay, what does that mean? Okay, so it has got polynomial time and it's got non-deterministic. So let's start with polynomial time first. Okay, it's a notation that we need to talk about in this class, but I have not introduced it yet. But to be the quickest way to describe it is the amount of time it takes to solve a problem is proportional to the polynomial, to a polynomial of the size of the problem. Okay, so if the size of the problem is represented by n, okay, it doesn't matter what it is, but n as a number, then if the amount of time to solve the problem is proportional to n squared, it's polynomial time. If the amount of time it takes to solve the problem is proportional to n cubed, it's polynomial time. Oh, what if it is n to the power of 512? That's a pretty bad scaling, function. It is still polynomial time, as long as it is contained by n to the power of some constant number. It is polynomial time. Yep.
Would it be related to the big O?
Yes. So we're going to get to the big O, but this is a kind of like a quick preview because I want to explain what is NP. So that's polynomial time. So bubble sort is polynomial time. Insertion sort is polynomial time. What else is polynomial time? Convolution is polynomial time. Okay? So all of those things are polynomial time. So it's not really complex as a concept because you're just basically saying, if I raise n to some power, that becomes the upper bound of, how bad or how much time it takes to solve the problem. Non-deterministic is the fun one. Non-deterministic is basically saying, assuming you have a magical processor that can spin off as many cores as you need, then it will be polynomial time. So we are not talking about quad core. We are not talking about hexa core. We are not talking about octa core. We are talking about potentially infinite core. Okay, every time you need a new core, magically a new core appears and it can run at full speed without slowing down any of the other cores that are already active. If you have a magical processor like that, then it would take only polynomial time. That's NP. Is that okay? So in the traveling salesman problem, if I give you 5 cities, how many ways can you traverse those 5 cities, assuming it is fully connected? You got 5 choices for the first city, 4 choices for the second city, 3 for the third one, and so on. 5 factorial. Okay, doesn't sound too bad. 5 factorial is 120. What about 6 factorial? 720. 7 factorial is 720 times 7, and so on, right? So as it turns out, it doesn't scale very well. Yep.
So the problem is that each path would need a
Polynomial time. Exactly.
So I'd have to have n factorial forms
Yes.
in order to solve it.
Yes.
And then there would be polynomial.
And then it'll be linear time, in fact, to figure out the actual distance or the actual length of that path. And then you have to pick the shortest one. But picking the shortest one is not going to be proportional to the polynomial time, because as you find, you can basically have those things to compare to the next available one, so you can actually get to the answer pretty quickly. So that's why it's an NP hard problem. It's all pretty theoretical. Sounds like doesn't relate to anything that you might actually need when you go out there and become a developer and get employed. Well, I can tell you that it has everything to do with what you need to know in order to secure your job. Okay, so here's the deal. Let's say you're working for a pizza place doing pizza delivery, okay? And your boss says, our customers are always complaining the pizza is not hot, it's getting cold because it takes too long to get to their place, and so on and so forth. And your boss says, oh, I know you have taken a few computer science classes. Can you write me a program that can find the shortest path to do pizza delivery? You go like, yeah, I can do that. Because I understand what is, experiment without replacement, right? Because that's how we end up with a factorial, right? And you go like, yep, I can just modify that program the Omega program that I wrote in cisp440, and I'll be able to find all the paths and just figure out which one is the shortest. Cool, not a problem, right? In pizza delivery, with a single pizza delivery truck or car or whatever, how many destinations do you think it has to handle? Per trip, yes. So every time you get out of the pizza shop, how many stops is going to be on your way? 4 or 5 seems reasonable. Okay, so you're looking at 5 factorial, which we already know is 120, and you pick the shortest one, and you're done. Exploring 120 paths, each one only having 5 destinations, is not too bad. I mean, you can probably get it done in less than a millisecond with these processors that we have. So the pizza place is hugely successful because now the pizzas are delivered as quickly as possible. Your boss is really happy. One day you go to work and your boss says, you're fired. Why am I fired? Well, because 1, you embarrass me, and 2, your program doesn't work. You go like, what? It's been working for months. What do you mean? And your boss said, the program works so well for us, I decided to share with, a delivery truck company like UPS and FedEx and stuff like that. And then the program just kind of hung up. Nothing happened. Didn't give us an answer at all. And the computer almost burned up. Then you go like, well, that sounds kind of interesting. And then you remember about scaling, right? You go like, so what is the number of stops that a typical delivery truck has to stop, on a particular day? Your boss says, well, maybe 100 or so. Then go like, so that means the algorithm has to explore 100 factorial different paths. Then the boss says, it can handle 5, so If you can do 5 in a millisecond, of course your boss doesn't know what a millisecond is. So if you can handle 5 in a millisecond, 100 should take only 20 milliseconds. You go like, no. It doesn't work that way. Okay, it's basically the ratio between 5 factorial and 100 factorial. So you go to a spreadsheet, right? Because a calculator would have overflown already. So you go to a spreadsheet. I cannot use that one. I can use that one. So you go to a spreadsheet and you go like, okay, does it have factorial? Yep, it does. I think that is factorial. Then you go like, boss, we are looking at this number divided by 120. That is the factor that you have to increase. It's like, okay, so we can do the calculation, okay? So we have 120, and so we are looking at this number divided by this number, and then we want to multiply that by a millisecond, 0.001. So we have 0.001 times this number. This is the number of seconds it takes to finish the computation. Okay? So you say, okay, your boss says, okay, I don't understand this many seconds. Okay, tell me about hours. So you go like, okay, if this is the number of seconds divided by 3600, that's the number of hours. The boss looks at it and go like, I still don't get it. Okay, fine. Let's express it in days, okay? Divide this number by 24 because there are 24 hours in a day. You go like, okay, this is the number of days. I still don't get it. How about years? I can give you years. Okay, fine. Okay, I'll give you years. So that will be this number divided by 365.25-ish, okay? Because how many days or how many auto rotation around the sun is a irrational number. So, 0.25 is kind of like a close estimate. So you're saying to your boss, this is the number of years it will take to finish. You go like, no, I'm still not getting it. Okay. What about centuries? Exactly. So there's not enough time to actually do it. Okay. Well, the universe is, according to theory, the universe is what, 14 billion years old or something like that. This is way over 1 trillion years. So that is why it's going to be helpful. Okay, now this is not the helpful part yet. Okay, so because your boss is going to say, oh, that's only because you're dumb. You're writing an algorithm that would take this long to finish. Then you go like, no, boss, listen to this. This is called an NP-complete problem, which means it is a problem in a class of problems that are equally difficult to solve. Fine, okay, I'm going to hire another person to solve this problem then. Then you go like, oh, but all the computer scientists, all the mathematicians have tried this and nobody has discovered a faster way to solve these problems. Yeah, sure, you can fire me, but the next person is very unlikely to solve this problem either. Because if that person can't solve the problem, that person is not going to work at a pizza place. So that is why understanding NP-complete can be relevant to your employment. Now, I'm serious about that, okay? Not quite the pizza shop part, but understanding complexity and what an NP-complete problem is really helpful, because a lot of optimization problems are actually NP-complete in nature. So when you're talking about compilers, okay, because some of you are taking assembly language programming, which means you are the organic compiler, right? So in compilers, okay, so let's say you have a lot of registers. The toy processor that I have only has 4 registers, which means there's not really a whole lot of room for optimization. But let's say you're working with a real processor, and let's say it has 256 registers. So now the question is, what do you keep in registers and what do you not keep in registers? That is still an optimization problem. As it turns out, most optimization problems are NP-complete. Okay. Do you guys know that the Intel processor or the AMD 64 architecture has multiple ALUs, and you can change the order of instructions and it can change the utilization of the ALUs behind the scenes. So that's an optimization problem too. It's like, okay, I know I can add, I can subtract different things, and then I can use the result of those two operations for this and so on. But how you order the instructions can impact how the ALUs are getting utilized in the core. And to figure out which combination or which sequence of opcode will give you the best utilization of the ALUs inside the core is an optimization problem. And it by nature is NP complete. It just doesn't have a very large base number. So it's not 100 factorial, maybe 5 factorial, 4 factorial, or something like that. But that tells you, the problem or the solution cannot scale. Okay? So all of that stuff is important. Okay? Now, in computational complexity classes and whatnot, they will actually help, tell you how to derive these numbers. So practically speaking, when you become a developer, you probably won't be deriving the numbers because it's not likely that you'll be coming up with a new algorithm, but understanding the complexity and choose your algorithm accordingly and understand whether a problem can even be solved practically is important. That is the application of NP completeness. Is that okay? So I kind of digressed because we were talking about Dijkstra's algorithm, and then we kind of segue into the traveling salesman problem, and then we got into the NP complete issue. Yep.
Is it sort of similar to, here's the server, and you're, for example, CSGO player, and your X has to go through a bunch of servers until it gets to the main server, and find the fastest way to minimize the ping.
That is done by communication between the routers. So
Is it sort of the same concept?
it is kind of the same, but the between the routers they have communication protocols, so that between the routers they can figure out how to do load balancing and get the traffic through and increase the throughput as much as possible. But you're correct that it is a similar problem when you're only looking at one single packet. But the problem is actually much more complicated than that because you're not the only one using the internet. So now the question is, what are other people doing so that they can determine, okay, the destination IP address is all the way over there, and then we got all of these interconnected routers in between. How should this packet route? That becomes an interesting question because it's dynamic. It's never fixed. Okay, from one moment to the next, things can change dramatically, and then the routers have to respond to that. So that's an interesting question because it's related to what we are talking about, but it is actually much more practical, and it is also much more difficult to solve because of the dynamic nature of network traffic. And a router can go down. Okay, once a router go down, that changes the equation entirely. So how do you deal with that? So that's a good question. I'm pretty sure networking companies spend a significant amount of research in this kind of area. All right. Well, we are running out of time, but I'm hoping that you get something useful out of this. Next time you look at the pizza, okay, it's not going to be the same anymore.